In this video, we're going to look at linear functions from data. So previously, we created some linear functions with word problems, and using what we know about the situation, we created those algebraic equations. So now what we're going to do is we're going to create linear expressions, linear equations, and linear functions from data. The way we do that is we collect some data, and we collect data on two variables. One variable we'll call the x, and the other variable we'll call y. Now, x is our input variable, y is our usual output variable. That doesn't necessarily mean that x is causing y, but it is the convention that we use. We use one variable as x, other as y. Let's look at an example. Now, the source for the data that you're going to see on the next slide comes from here. It is about oil consumption per year. We're looking at the years from 2009 through 2015. World consumption in billions of barrels of oil. You can see that in 2009 it was about 31.42, and then generally it moves up, and in 2015 it was 35.06. One of these variables, the year or the oil consumption, is going to be called our x. And what I will use the x as the year. The world oil consumption in billions of barrels, I will use as the variable y. With that convention, we can plot points on a scatter plot. So we're going to create points on the Cartesian coordinate plane that match up with our data. So for instance, in the year 2009, there were 31.42 billions of barrels of oil. So we'll plot that as a point, 2009, 31.42 on our scatter plot. And I'll do that for every single year. I've already done that and created this. This is just a scatter plot I've created in Excel. But you can see each one of the points for each year. 2012 was somewhere between 33 and 33.5 billions of barrels of oil. 2015 was just above 35 billions of barrels of oil. Now, here's what we're looking for. We're looking for a pattern. And in particular, in this section, we're looking for a linear pattern. This does look fairly close to a line. It's not a perfectly straight line because obviously there's some variance or some deviation, but it is matching what we would expect with a linear pattern, or fairly closely matching a linear pattern. Once we see that our data matches fairly closely with this linear pattern, then we can create a regression line that best fits the data. We use technology to do that the vast majority of times. There is a way you can do it by hand, but it takes more time by doing this by hand. So the line that best fits the data is something that we're going to find using technology. That line is called the least squares regression line. I'll talk about what that least squares means in a moment. Along with that line is going to come a correlation coefficient. And if we're trying to fit a linear pattern to our data, that correlation coefficient is called a Pearson correlation coefficient. It's always labeled as the letter R, and its values are between -1 and 1. Once again, technology will give us that Pearson correlation coefficient. How R works is the closer it is to 1 means a strong positive linear relationship. So the stronger positive linear relationship lines give R values close to 1. The strong negative linear relationship gives R values close to -1. By the way, when I say strong positive linear relationship, I'm saying the line fits the data well and the line has positive slope. Strong negative linear relationship, I'm saying the line fits well, but the line has negative slope. So closer to -1 and closer to 1 are the better fit values. And if we're close to 0, then it's not a good linear relationship. It might be a different type of relationship, but it's not good at being a linear relationship. In the book that I typically review, it has this picture that I typically use for my class. We have these pictures. A perfect 1 is a line whose has positive slope. All dots fall on the line. A 0.8 means we generally have that pattern as we move right, we're moving up, but all the dots don't fit on a line. And the closer it is to 0, the less pattern there is. So you can see at 0 itself, it just looks like a bunch of dots almost in a circle. You can see some other values of 0 as well. Here we have sort of a W shape. That's going to also have a value that's really, really close to 0, or a square with a bunch of dots in it. That's a close to 0. So all of these others, there are patterns here, but the linear pattern would be close to 0. And just so we're all on the same page, when we say +1, it doesn't matter what the slope is. The slope may be 20, it may be 1, it may be 13, it may be negative, excuse me, it may be 1/2. As long as we have positive slope, the R value is a 1. As long as we have a negative slope, if it's a perfect line, then the R value is -1. So that's kind of a good reference about how these R values work. Now, at some point, we're going to be asked whether or not our least squares regression line fits the data well, or whether the data fits the line well. You can phrase that in either way. And we just said, well, if the R values are close to 1, or if the R values are close to -1, the data fits the line well, or the line fits the data well. But how close do we have to be to 1? And it turns out it kind of depends on a variety of factors. One of the factors it's going to depend on is how much data we have. Another factor that it might depend on is what situation we're in. If we're in a physics situation, we may want our R value to be above a 0.9. If we're in a social science experiment, our R value may be able to be like a 0.3. and still be a strong linear relationship. Now, so in other classes, we may have different R value cutoffs between a good and a bad relationship. For this class, the one I teach, we're going to always make the cutoff at 0.75. Therefore, if R in absolute value is above or equal to 0.75, we are going to say there's a strong linear relationship. And if R in absolute value is less than 0.75, we will say it is not a good linear relationship. So for this class, it's going to be 0.75. But again, if you move on into some other class, it may have a different cutoff value on your R for between a good and bad fit. Now, the line that our scatter plot gave was this one. Y equals 0.5611x minus 1095.6. And it also gave an R squared of 0.9847 and an R of 0.9923. R squared is just the squared version of R. So our R was 0.9923, and I got that using Excel. That was the R from this data set. And you can see that this is a really, really close to a line. If I draw a really nice line through that data, then it would look like it gets really, really close to all the points. And so that's why we get an R value, which is really, really close to 1. And so we would say that this line fits the data well because of the very high R value. I will show you how to get this using Excel in another example, but if I give you a problem to do on the test or a problem to do on the homework, this is something that I'll provide. Now, once we have that line, we can use it in the exact same way that we used our lines before. So we could say, once I know this line, which we got from technology, what would this line predict the oil consumption to be in 2018? When we do that prediction, all we have to do is plug in 2018 into our X. Our X was the year, if you recall. So Y is equal to 0.5611 times the year 2018 minus 1095.6. When I do that calculation, that's something we just type into our calculator. It comes out as 36.6998. And because all of our data was rounded to 2 decimal places, I'll go ahead and round this to 2 decimal places as well. That 69 rounds up to a 70. So the prediction is that the oil consumption in 2018 was 36.70. This was in billions of barrels of oil. And you could check that if you wanted to. You could, obviously 2018 is in the past, so you could check and see if that held true. Let's do another example. Here's the source that our data on the next slide comes from, or the source is, I should say. We were going to create a least squares regression line and give the correlation coefficient for the following data that we're going to see on the next slide. The data is going to show the Brady scorecard points from 2014 and the murder rates from 2016 in a sample of, I think, 10 states. So in 2014, here are the Brady scorecard points. You can see that Wyoming has a negative scorecard point of negative 28. Maryland has a positive scorecard point of 56. And generally speaking, the way Brady scorecard points work are that as the values get higher, that means the gun laws are stricter. So Maryland has stricter gun laws than Idaho, and Illinois has stricter gun laws than Indiana. So that's how you read that. Stricter gun laws mean higher Brady scorecard points. And then the murder rate is pretty straightforward. That's murders per 100,000 people. So that on average, how many murders per 100,000 people. And you can see these data. We're calling the Brady scorecard points the X and the murder rate the Y. Somebody could have also reversed that. But if you call Brady scorecard points the X and murder rates the Y, when you plot out each ordered pair, you get this scatter plot. So that first one was negative 28, 3.4. That's the point right here. And that point stood for Wyoming, I think it was. And then the point with the highest Brady scorecard points, or the state with the highest Brady scorecard points, was Maryland. There, this point out here. And so this is a lot less linear than our first example, although this still kind of has a pattern where as you move to the right, you're moving up. If you put this into Excel and ask it to give you the least squares regression line and the Pearson correlation coefficient, it'll give you these two things. It'll give you y equals 0.07x plus 4.65 and r equals 0.7723. That r of 0.77 for this class, since it's right above 0.75, we're going to say it's a good fit for this class. Other classes may have said used a different cutoff value for the R value, but we'll say it's good. And then we can use the line to do some predictions. By the way, what that line is, it's the line right here on the graph. If you actually graph that line, it looks like this. So does the line fit the data well? Yes, it does for our purposes, for R greater than or equal to 0.75. And then what would the line predict the murder rate for a state to be if the Brady scorecard points of a state were at 0? What would the line predict the murder rate for a state to be if the Brady scorecard points of a state were at 3? All right, so what would this line predict the murder rate for a state to be if the Brady scorecard points of that state were at 0? We take our line And knowing that the murder rate is the Y and the Brady scorecard points is the X, we just have to plug in 0 for X. And if you do that, it's pretty straightforward that this line is predicting the murder rate to be about 4.65. Where would this line predict the murder rate for a state to be if the Brady scorecard points were at 3? Well, in a similar fashion, we'd write in a 3 for our X value and then calculate what the Y value would have to be. When I plugged that in, I got 4.86. So this line would predict a murder rate to be 4.86 if the Brady scorecard points of that state were at 3. Now, just for the sake of completeness, I want to show you how I actually came up with the scatter plot that you saw and how I came up with the regression line and correlation coefficient with Excel. This is not something you'll have to do in my class, but I do want to point out where this information is coming from using technology. So here's my data. The data I've just simply copied and pasted from my table into this Excel sheet. Now I've highlighted my data. If I want to put in a scatter plot, all I have to do is go up to the insert and then down here to the charts, it says insert scatter plot or bubble chart. I'm going to insert a scatter plot. Oh, this is reading it incorrectly. Let me actually highlight. I think what's happening is I'm highlighting incorrectly. Let's highlight those two things. There we go. And then once I insert that scatter plot, it looks like this. Now there's a number of different ways we can, change this. I can put in any title that I want. I can also make this bigger or smaller, or I can change the axes. I can change the format by clicking on different values here. I can make it look slightly different. I'll just use our basic scatter plot, or at least one of the basic scatter plots. I'll use that one. And then each of these points is representing one of my states. So the Wyoming is -28 and comma 3.4. You can see it when I highlight the points. When I put my cursor over that point, here is murder rate where the point is -14.5, comma 6.5. So that's the Indiana point. And then if we want to put in a regression line, I can hit this plus and go to the trend line. Now, I'll do some more options here. You could just click the linear if you wanted to, but what's really nice is that when you put in the trend line, you can display the equation on the chart and display what's called the R squared on the chart. That's just the square of R. And when you do that, you get that line that I was referencing earlier. And an R squared, let's try to make that a little bit bigger. so that it's visible. There we go. So there's my line y equals 0.07x plus 4.65. I took off the last two decimals. And then the r squared is about 0.5964. If I take the square root of that, that's where I come up with my r. So that's just something you can do on Excel. You can move that around, make it bigger, do a lot of other things with it. Okay. You can also do it with a TI-84 calculator. I won't do that in this video, but there may be a companion video that shows how to do linear regression with the TI-84 calculator. But there you go. By the way, each of the predictions that we made was basically a point on this line. So when we said predict the murder rate when the Brady scorecard points were at 0, what it was doing, it was giving us this point on the line right here. And when we said predict the murder rate when the Brady scorecard points were 3, it was giving us this point on the line right there. So the line's points were doing the predictions for us, giving us those predictions. Now, will those predictions be perfectly accurate? No. Obviously, there's some difference between each one of the points and the prediction on the line. What the least squares regression line does is it minimizes the square of all of those errors. So it takes each one of the distances from the point to the line in a straight vertical distance. And some of these distances will be positive because the points are above the line. Some of these distances will be negative since the points are below the line. It squares all of those distances. And it's the smallest, the least squares regression line minimizes the squares of all of these errors. So that's what we mean by least squares regression lines. We're minimizing the least of the squares of all these errors. We want to minimize the squares because some of these are going to be negative, some of these are going to be positive. If I just minimized the error itself, some of the error is negative, some of the error is positive, then it would cancel out. So that's what we do. We minimize the squares of these errors. All right, let's do another example. So here's the sources of our data. We're going to examine if there's a correlation between the number of McDonald's restaurants per million people in a country and their overall level of happiness in those countries. So data was collected from a sample of 11 countries. You can see where those citations come from. And this is what we get. The number of McDonald's per million people, we're going to call the X value. And the overall level of happiness is a Cantrell ladder score. Not to get into the weeds, but basically a Cantrell ladder score is a measure of subjective well-being. So it's like a life satisfaction score. It's not how happy I am at the moment, but more how satisfied I am with life. And they collected that data in these 11 countries. Now, just like the previous problem, we could throw this information into Excel, have Excel give me a scatter plot, and then use the technology of Excel to give me the linear regression line along with the Pearson correlation coefficient. That's what I've done, so I'm not going to go through it again. I'm just going to state that this is what the scatter plot looks like. Notice that this doesn't seem very much like a line. There's not a lot of pattern to these dots. The McDonald's per million is on the x-axis. The Cantrell ladder score is on the y-axis. But there's not a lot of pattern here with these dots. And sure enough, when we create a least squares regression line, we get y equals 0.01x plus 6.66. And our corresponding Pearson correlation coefficient is 0.2163. Since this value of R is less than 0.75, we can say that this line does not fit our data well. So because the R value is less than 0.75 in absolute value, we say the line does not fit the data well. Now we can still use it to do predictions, although as a good researcher, I'd probably not use it to do predictions unless I was asked to specifically. Okay, because we know the predictions aren't going to be good since the line doesn't fit our data well. But if you run into this on a homework problem in my class or on a test in my class, and if it asks you to do the prediction, even if it's not a good line for predictions, so even if the line doesn't fit our data well, go ahead and do the prediction anyway. It asked us to predict the Cantrell ladder score if the country had 19 McDonald's per million people. So all we have to do is replace the X in our line with a 19. So that becomes Y equals 0.01 times 19 plus 6.66. Therefore, we get a Y value of about 6.85. Again, this prediction probably is not going to be a very useful one because our line had a really low Pearson correlation coefficient. So it was in the twos, 0.2 something or other. So there you go. Even though this is not a good line to predict with, we can still do it if a problem asks us to do it specifically. Now we've seen what a pretty low R value looks like. This is a scatter plot whose dots, when we've tried to create a line, we get a pretty low R value here. Low meaning close to 0. Let's look at a couple of other examples. Here's an example of the number of abortions in the US per year. And this comes from the Michigan Health Statistics, the state data. So if you look at the number of abortions per year from 2009 to 2018, you get this. Now this is in thousands. So this is 789,000 in 2009. And then it's going down 2017 had the lowest number of 613,000 abortions. And we get this pattern. It kind of looks pretty linear up until maybe 2016 and then kind of flattens out. So I'm guessing that this R value is going to be negative because it looks like it's declining, the number of abortions per year. Looks like it's declining, so it looks like the R value is negative, meaning the slope of the line is also going to be negative. Now, before we state anything, I do want to mention you can use your x-axis like I did right here as the years themselves. So 2008, 2010, 2012, you can see all the year numbers. Or you could actually, instead of using an x value of 2008, you could use an x value of 8, and therefore every year, 2000 and something, is just represented by x value of whatever that something is. So here, 2008 is represented with an x value of 8. 2010 is represented by an x value of 10, and so on and so forth. 2018 is an x value of 2018. This is going to give you a slightly different line than this one, although they're going to give the same predictions. So let's look at both lines. If I use X as the year since AD0, so that means 2008 is in fact used as X value of 2008, then I get this line, Y equals negative 20.13X plus 41,206. And my R value is negative 0.9606. If I use the X value as the year since 2000, most of the components of my line and Pearson correlation coefficient are going to be the same. My Pearson correlation coefficient is exactly the same. It's negative 0.9606. So whether you use 2008 or whether you just use 8, your R value, the fit of your line, is going to be exactly the same. Also, the slope of the line is exactly the same as well, negative 20.13. The only difference is where we start our value, our y-intercept, so to speak. If I use X as year since AD0, then the Y value up here is 41,206. If X is the year since 2000, then the Y value is 951. To me, the Y-intercept value is 951.22. Again, both cases have the same R value because they're both going to fit exactly the same way. So our next question is, based on this information, does the line fit the data well? Since the R value is negative 0.96, in absolute value, that would be a 0.96, which is above 0.75. Therefore, this data does fit our line well, and vice versa. Our line fits our data well. The negative on the R just tells me that the slope of the line is negative, which we can see from the line itself. And then we can use this line to do a prediction of the number of abortions in the year 2020. What I'm going to do is I'm going to use both lines and see how the calculations turn out. If we use X value as the year since 80, meaning 2020 stands in for 2020, then what I would do is I'd write Y equals negative 20.13 multiplied times the year 2020, and then add 41,206 to that. The Y value, therefore, becomes 543.4. That's again in thousands of abortions. If we use the X value as the year since 2020, then the year 2020 stands for the X value of 20. And I would calculate in the following way. I'd say negative 20.13 times 20 plus 951.22. And then we do the calculations and we'd end up with a Y value of 548.62. Now you might say, well, these two didn't give me the same answers. They didn't give me the same answers exactly because I was using rounded numbers here for both my coefficient of X, but more importantly, my y-intercept. If I wouldn't have used rounded numbers for this coefficient of X and for this y-intercept, then they would have matched up perfectly. Again, using rounding numbers, rounding to 2 decimal places, and then multiplying by an extra 2,000 makes a little bit of difference there. Not just a little bit, quite a bit of difference there. So that's the reason. So this rounding of this coefficient of X and the rounding of these y-intercept values. Now, I want you to notice that obviously abortion is a controversial topic. And when we talk about controversial topics, sometimes you can get into controversy. Sometimes you can avoid controversy. Hopefully, in this case, we're avoiding any controversy. We're not talking about whether or not this was moral or immoral or anything like that. We're just calculating the numerical values with it. So if somebody were to take our data and take our linear regression and then do some other moral implication argument about that, then it could be we could get into the morality of things. But we're avoiding that in this example. We're just calculating the numbers, and you can take whatever moral stance you think about that idea. The same was true with the previous example where McDonald's and Cantor ladder score versus, and also the example before that, which was guns and murder rates. Let's do one more example like that. Let's look at some data on Michigan marriages per year. Again, this comes from Vital Health Stats, the Michigan at michigan.gov. So this is marriage and divorce rates up to marriage rates up to 2022. Okay. So in the state of Michigan in 2014, there were 57.1 thousand marriages. And then obviously it goes down a little bit, goes up a little bit for a couple of years, and then down. The lowest was at 2020 at 42,000 marriages, roughly. These are rounded numbers. And then it went up after 2020. So you can see that the number of marriages has fluctuated from year to year. It looks like this if we draw a scatter plot. 2014 up here went up a little bit, and then it goes down. And then there is this kind of weird deviation in 2020 because of COVID lockdowns. And again, that's just what happened. So if I were to look at that, what would I guess the R value is? If I were to look at this scatter plot, well, in general, over time, it looks like it's going down, but it's not really a strong correlation. It doesn't look like a straight line. There's some weird arch here at the beginning, and then there's like a fall down. So if I were to guess the R value, it does look like it's going to be a negative, but it's not going to be a really huge, it's not going to be real close to 1. It's also not going to be really close to 0 because this is not just a bunch of random dots. It turns out the R value in this case is a negative 0.7176. Again, not a perfect fit. It's close to being a good fit for our class, but it actually falls under that threshold of being a good linear regression model. So the line would not fit the data well because this R value is under 0.75 in absolute value. And we can do that for lots and lots of other things. Okay. Notice that in example 5, that's all I was doing, just looking at the R, looking for the R value. Okay. Now, I don't expect you to be really super accurate on your R value. If I give you a question asking for an R value, I'm not going to give you something that looks like the difference between 0, or excuse me, between a 0.68 and a 0.72. That's not very fair. But I could give you a question that says, does this look to be closer to an R value of 0? Does this look closer to an R value of 0.7? Or does this look closer to an R value of 1? And that's what we'll do in each of the cases in example 6. We're going to guess at what the R value is. We're not going to be real concerned of being super duper accurate, but we should know generally what the R value does in each case by just looks. So if I look at this example, this is a very nice scatter plot, and the points are in a pretty straight line. They're not exactly in a straight line, but they're close to a straight line. So I would guess that's going to be close to either -1 or 1. And because it looks like the slope of that line would be positive, I'm guessing that R value is pretty close to 1, like a 0.95 or a 0.9 or something like that. So somewhere like 0.9-ish on this example. If the R value actually comes back at 0.89, That's not a big deal. That's, again, that's not the type of accuracy we're looking for. Let's look at another scatter plot. Here's another scatter plot. These points are all over. Kind of looks like they're all engulfed inside of an oval shape, but it doesn't look like a really nice straight line through these points. I would guess that the R value here is pretty close to 0. Maybe it's a 0.1 or negative 0.1, but I bet you that's R value is pretty close to 0. So in this scatter plot, this shows an R value pretty close to 0. Pearson correlation coefficient should be pretty close to 0. How about in this one? Well, this does look like there's a linear pattern. That linear pattern looks to me like it has a negative slope. So the R value is going to be negative. It's not as close as our first example. All the points weren't quite as close. So maybe I would guess that this is going to give me a 0.85, a negative 0.85 as my R value. Excuse me, I just said it was going to be negative. So maybe this R value is negative 0.85. Could be like negative 0.9 as well. But I'm guessing somewhere in there. A good correlation coefficient, a good fit, but with a negative slope. So good fit with a negative slope. Once we've done some predicting of those R values, we have to take a couple of notes on actual predictions. So the types of predictions that we were looking at earlier, not trying to figure out what the R value is, but just doing a prediction. And I want to take a moment to talk about the idea of extrapolation. Once we've created these linear models from data, it's very easy to do predictions. And if we do our predictions far enough away from where our actual data is, so when we do predictions outside of known bounds, that's called extrapolation. Interpolation is when I predict inside of my known bounds. When I start predicting outside of known bounds, that is not a good thing to do. Oftentimes, the linear model that I have will break down when I do predictions outside of known bounds because the model may no longer apply there. Remember way back in example 1, we had a very good line. The line fit our data really, really well. And we were looking at years between 2009 and 2015. Well, if we tried to predict 100 years away from this, if we tried to do a prediction in the year 2015, that would probably be 2115, excuse me. If I tried to do a prediction in the year 2115, this pattern is almost definitely going to break down because of a couple of reasons. Because of, being able to use oil, and also, we might have new technologies. We might have some of the known oil reserves in the world go dry. Who knows what's going to happen 100 years out with new technology? Maybe there won't be a need for oil 100 years from now, or 100 years from 2015 even. So be careful on doing extrapolation. You don't want to predict outside of known bounds. It's really nice to predict between 2009 and 2015 here, but when you try to predict at 2115, 100 years beyond what our data is, that's probably going to be a very bad prediction. And there's famous examples of where extrapolation has gone bad. One well-known famous example is a guy named Thomas Malthus, who predicted that the world was going to run out of food to feed the growing population. And well, long story short, his models broke down because he was predicting way outside of his known bounds. And he wasn't expecting technology and food crops to be more productive, and so on and so forth. So don't extrapolate. You can learn more about Thomas Malthus if you want. It's a very famous prediction. Another thing that I want to mention where we can get bad results is if we do data manipulation. If I'm a researcher and I start throwing out data that I don't like, I can easily get a model that says whatever I want it to. Let's talk about an example that we saw earlier. We did an example with McDonald's restaurants and the happiness level measured by a Cantrell ladder score. And we saw that the R value here was like 0.2163. That means these two variables don't seem to be in a pattern. We would say that these two things are not correlated because the R value is too low, it's close to zero. And we would guess that the number of McDonald's restaurants per million people really doesn't have any effect on the happiness level or the Cantrell ladder score. Now, if somebody were to manipulate this data, they could easily manipulate this data by getting rid of points that they don't like and just focusing on data that they do like. Imagine that the only data that you focused on were these 4 points here. Well, then you'd think as the McDonald's restaurants per million people go up, the happiness level is going to go down. And you could do the same thing in reverse as well. Let's say you only focused on these points here. Well, these points are going to form a really solid line with a positive slope. The R value is going to be pretty high. and the slope is going to be positive. So if you just focused on those 5 points, then you would walk away thinking, yep, as the McDonald's per million people goes up, the overall level of happiness is also going up. So if you focus just on data that you like, or that you ignore stuff that you don't like, then you can kind of paint any narrative that you want. That's why it's so important that when scientists do research, they don't throw out data that they don't like or that they don't expect. They should never throw out anomalies. There's been some famous examples of scientists who have manipulated their data sets to give themselves a stronger paper, and that's very unethical. We shouldn't manipulate data just to get the result that we want to get. And again, there's been very famous examples of that happening. So that's the end of this section on linear functions from data. If you want to learn more about how to use the TI-84 to do linear regression, you can. I know I went through doing linear regression on Excel pretty quickly. That's not the focus of this class. The focus of this class is once you have the line, once you have that Pearson correlation coefficient, can you state whether the data and the line fits together well, or can you do some predictions using that line?